The term dynamic equilibrium on our slide 84 it says in a closed container, and that's key, my friends, closed. When we have a lid on it, we can reach something known as dynamic equilibrium, and it's simply two opposite and opposing forces, indeed in equal rates. The rate of vaporization, liquid going to gas, is occurring at the same rate as condensation, the gas coming back to liquid. The total amount of vapor and liquid will not change, although there is a continuous process of the phase change occurring. They're still occurring, but at equal and opposite rates. So there's no net gain or loss of either the vapor or the liquid, although the processes are indeed occurring. Whenever we have two opposing processes, each occurring at the same rate with no net gain or loss of material, we refer to that as dynamic equilibrium. And actually, the title of our next chapter is all about equilibrium, with a forward and a reverse reaction occurring at the same rate. It does not mean that there's equal amounts of vapor and liquid, but it means that they are changing by equal amounts. I clearly might have more gas than liquid or more liquid than gas, but the phase changes are occurring together. That's a previous slide. So here's a visual for our dynamic equilibrium. In a closed container, clearly with a stopper, the first approach is when I first take a flask, and let's just say this is water, 2 H's and an O, looks like the structure, and I first put the lid on, the little rubber stopper here. The liquid will turn to a gas. If the lid were off, it would just escape away and we could not set up an equilibrium process. But the first process is that the liquid turns into a gas. And you can see as those gas molecules escape, they themselves could gain enough kinetic energy and go back to the liquid form. When the rates of liquid to gas, gas back to liquid are indeed equal, we reach dynamic equilibrium. That term, called vapor pressure, is how we measure the amount of vapor, the amount of gas phase on top of its liquid. When we have an equilibrium occurring between the liquid and gas phase, we call that vapor pressure. Remember using Dalton's law of partial pressure? Back in our gas chapter, we said that the total pressure is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 and so forth. We account for the pressure of the water vapor when collecting gases by water displacement. In other words, the total pressure inside of a collected chamber, we had to subtract out the contribution of the water before we did our PV over T's. The weaker the attractive forces between the molecules, the more vapor we'll have. So the fewer London dispersion forces or dipole-dipole forces the less attractive molecules have for each other, the more gas that will form. Therefore, weaker attractive forces have a higher vapor pressure. Volatile liquids escape from liquid to gas very quickly and have a very high vapor pressure. Back to this picture a moment. If this indeed is the gas phase sitting above its liquid, whenever the vapor strikes the surface, it creates a pressure. The more particles in the gaseous phase, the more collisions, creating a higher pressure. Volatile liquids have a high vapor pressure. Volatile liquids tend to escape from the liquid phase very quickly. So in the vapor-liquid dynamic equilibrium, if the volume of the chamber is increased, we'll decrease the vapor pressure. Remember that that would create fewer collisions if we actually gave them more area to move around. Therefore, for a period of time, the rate of vaporization will be faster than the rate of condensation until we have actually reached back the equilibrium. So if I change the volume, it needs time to reestablish the equilibrium, but over time, it indeed will come back to where it was before. So changing the container's volume, it disturbs the equilibrium, but over time it can achieve the dynamic equilibrium again. And that's what they're showing here using a piston. If this is the original volume, The rates of vaporization and condensation are equal, and the system is at dynamic equilibrium, up arrow and down arrow at the same magnitude. But if I pull out, pull out on the top of the piston here, increasing the volume, the gas phase has more room to move around. Therefore, we drop the pressure. Notice how the vapor pressure has decreased in the size of the magnitude of the arrow. Give it time, and it would reestablish a dynamic equilibrium. Same is true here. If we push down on the piston and I decreased the volume, notice here the vapor pressure increases with a decreased volume. Boyle's law. Pressure and volume are inversely related. Smaller area, more collisions, higher pressure. But again, over time, the equilibrium would reestablish. So dynamic equilibrium is a system in dynamic equilibrium can respond to changes in the conditions. When conditions change, the system shifts in position to relieve or reduce the effects of the change. Next chapter will refer to this as Le Chatelier, he's French, Le Chatelier principle. A system at equilibrium will shift if I disrupt that equilibrium to get back to the state that it was once at. Dynamic equilibrium. When conditions change, the systems will shift to relieve or reduce the stress to that change. More coming with Le Chatelier's principle next chapter. Suppose we increase the temperature. Increasing the temperature increases the kinetic energy of those molecules, and we'll have more and more of those molecules able to escape the liquid and turn into the gaseous phase. So as the temperature rises, more liquid turns into gas, the vapor pressure will also increase. Vapor pressure is the pressure pushing down on the surface of the liquid. More gas molecules pushing down, the higher the vapor pressure. Even small changes in temperature can make a big change in the vapor pressure. So that rate of growth depends on strength of the intermolecular forces. If the molecules are strongly attracted to each other, it will take a larger temperature change. If the molecules are weakly attracted to each other, a slight temperature change will cause a bigger difference in the vapor pressure. The normal boiling point of water at 100 degrees Celsius. Normal is indicating standard pressure, which for us is 1 atmosphere or 760 millimeters of mercury. And the other unit there from our gas laws was 101.3 kilopascals. Those are all values for what we called standard pressure.